Hi, this is the third lesson of the third unit on physics use case, and we'll describe a little bit of details on statistics of events with normal distributions, which underlies a lot of what's seen when we do the proton-proton collision analysis for the LHC. So we first have to do what I promised you. We're going to define the independent, identically distributed random variables, because that's definitely what you get in physics. There is no doubt that each event is independent. There's no chance that the protons will remember from one event to another. And this is built into quantum theory. We will come back to these distributions, Poisson and binomial. And because the events are very unlikely, you can actually use either distribution. But as I said, every event is independent. That's rigorous. So we have these huge numbers of events, and each of them is independent of the previous. And so we get a lot of independent, and they're all identically distributed because they're all governed by the quantum mechanics of proton-proton collisions. And this is the typical, if it's not true, at least it's assumed to be true in most big data cases. I mean, if I do something like a survey, then they may not be independent. If I actually walk down the road asking people's opinion, then probably there's a correlation between the opinion of the person in house number one and the opinion of the person in house number two, because they'll probably come from a same social economic strata, and there's going to be a strong correlation of opinion with strata. So that type of event gathering will not give you obviously independent events, although they will be independent in some ways, but not fully. Whereas physics is independent, at least unless there's something fundamentally wrong with quantum mechanics and so on. But we're not going to assume that. We're going to assume quantum mechanics. All right, now we have the law of large numbers. And that's very important because we want to add up the results from lots and lots and lots and lots and lots of events. And so that requires adding numbers up, because the numbers are going to be for any histogram, and the number is for each event. It's either 0 if the event is in the histogram bin, or 1 if it, 0 if it isn't, and 1 if it is. And so this is very important to be able to add things up. And most of the statistics we need for the physics experiment corresponds to what happens when we calculate effectively mean values, or just simply the sum of lots of observations. So that's what this thing here says. We have the sum of n observations, and we either take the sum or we take the mean. Let me give myself a little pointer here. So we want either the sum or the mean. Typically, we're going to take the mean because the sum grows in size as we increase the events, and typically we're looking at effects which are probably better thought of as means, but it's sort of trivial. Anyway, if this thing here, which is I labels event, this x is here a number. It could, in practice, in the physics case, be a vector within a very high dimension. Then we're already looking at one component of that vector. Then we know that if I take this sum, then the expected value of O is n, the number of items in the sum, times the mean of each item, which is the same for each item because they're meant to have the same distribution. And that's sort of trivial. Here's something that's not so trivial, although not difficult to prove, that the error, or the standard deviation of this observable, is the square root of the number of events times sigma, where sigma is the standard deviation of x. All of these x sub I are drawn from the same distribution. This has this result we've already commented on, that error over mean goes like 1 over the square root of n. So this is what it means why this field is really hard. The amount of effort, the amount of time you have to run that accelerator and get those protons to run around is n is proportional to time. So it says that the error of the mean is 1 over the square root of the time. You have to run 4 times longer to reduce the errors by a factor of 2. Another thing you can do, which is probably better, in some cases you will do, is you'll improve the quality of the accelerator so it collides more often. Therefore, gives you more interesting events. Or you improve the measurement accuracy of the apparatus. Remember, for the Higgs, I noted that the width of the Higgs, which was around 2 GeV, on the observation was entirely due to measurement error, because we're measuring the momentum of the photons or leptons from which it decays into, and that the quality of the, people have they put $500 million into each of those apparati, but it's still true that it's only $500 million, so it's certainly not perfect. And you do the best you can with the money you have, and a very great effort is made to measure things as accurately as possible, because when we do signal over background, and as we showed actually in our Python experiments, the narrower that signal is, the fewer events we need to see something significant. So that's another way of making progress. So as we pointed out, this is sometimes called, I call this counting experiments or event-based experiments. Say cover surveys, and we already gave this example of the yes/no question. Yes/no, does it fall into a particular bin of a histogram? In the survey, people will ask them yes/no to will you vote for some person for a particular office. So then the error, if you measure n events, then the error is the square root of n. And also there's what you observe is distributed with a normal distribution, Gaussian. Actually, you only typically in the physics or even the survey case, you only do one experiment, so you don't actually usually measure the Gaussian distribution. You still use the results as Gaussian to measure the probability that your measurement is off from the real value. However, if we use Python, we can do something different. We can actually do 40,000 experiments. So we're going to measure 40,000 times. We will do that by generating 1 million events and divide them into 40,000 different bins, and we will plot the number of events in each bin. We will find an answer that has a mean of 25 and an error, which is the square root of 25, which is 5. And the next few slides will tell us how to do that. So this gives you a histogram, and that's shown here for 25 events counted for 40,000 times. Here is 25. This thing is so-called 1 sigma array, so it's 30. And this is 1 sigma away the other side, that's 20. And I like to stress that you have 2 types of square root of n here. We have square root of 5 this way, and we have around the square root of 3,000 here, because there are around 3,000 answers for 3,000 counters of the 40,000 got are in this bin and on this bin. And the square root of 3,000 is whatever it is somewhere around between 50 and 60. So we have 2 square roots. We have a square root for the number of events in each bin, and we have a square root for the width of this distribution. This graph here points out that if we go to the above 30, this region here is 30 up here. Then actually this red curve here, which I didn't actually discuss on the previous slide, is the so-called normal distribution. And we, as I stated, most things in life have normal distributions. This particular case, because 25 is not a very big number, doesn't exactly agree with a normal distribution, but it's pretty close. Look at this graph here. It's the red and the green curves are pretty close. However, you will find that below 20, the green curve systematically lies below the red curve, and above 20, it lies above. And that's shown here
we have the real estimate of the errors, and you can see the green curve is above the red curve by amount, much greater than the errors. So there is a systematic shift here, which is just not important, because you tend not to look at things in this detail. You don't usually take 1 million people in your survey and get such good statistics. So as I said, we would get this if we asked 1 million people a question with 40,000 answers, or if we took 1 million physics events, each with 40,000 outcomes, each equally likely. So either of those cases is governed by this simple case. Here's what I pointed out, that if you look at the middle of the distribution, 24 to 25 and 25 to 26, the red curve expects 3176 events in each of those bins. We observe 3179 and 3132 from our Python code, which is certainly within the square root of 3176, which is 56. So near the middle of the curve, which is really what counts, because that's where most of the data is, we get good agreement between the normal distribution and my Python experiment.